In this lesson, we're going to talk about Newton's third law and then move on to a more realistic way of dealing with friction. I'm going to give you a little thought experiment first for Newton's third law. Imagine I was to punch you in the nose. Okay? You would obviously feel a force. Your nose would go backward in your head, and it would hurt. It turns out that there's also a force on my knuckles. I can feel your nose hitting my knuckles, and that would cause my knuckles actually to decelerate. So there's a force there also. It turns out that any time I put a force on you, you put a force back on me. Forces always exist in pairs. And Newton's third law is that for every force there is an equal and opposite force. The trick is that they're equal. Going back to the nose and fist example, you might think that there is more force put on your nose because it hurts more, but it turns out that they are equal forces. It's just that your nose is a lot more sensitive and tender than knuckles are. So whenever there's a force, there's an equal and opposite force that opposes it. So for an example, a 70-kilogram man pushes a 15-kilogram child westward on a swing with a force of 20 newtons. What is the force of the child on the man? So we know that the force is 20 newtons that the man is putting on the kid. These numbers in here, the fact that the man weighs 70 kilograms and the kid weighs 15 kilograms, the kid is actually going to swing a lot more, the man doesn't really move very much, all of that is a distraction. Okay? They are equal and opposite forces. So if the force of the man on the child is 20 newtons west, okay, then the force the child puts back on the man is going to be 20 newtons in the opposite direction. Okay, so don't let the different masses distract you. Now, our next thing is going to be friction. Friction always opposes motion. So if the object is moving to the left, friction would be back to the right. Now, things that affect friction. One is the type of surface. There's a lot more friction on sandpaper than there is on an ice skating rink. And the measurement of the stickiness is called the coefficient of friction. And the letter we use for it is the Greek letter mu. It looks kind of like a curly F, something like that. So the stickier the subsurface is, the greater that value of mu or coefficient of friction is going to be. The second thing is the normal force. You don't have to draw this, but I kind of want you to see it. Okay, if I have a block on a table, okay, I could push it this way and there would be a certain amount of friction. But if I push down on it, I get more friction and it's harder to move it. The reason why is I push down on it, in order for it not to move down, the normal force pushing up has to get bigger, and that's going to give us greater friction. So the equation relating this is this: the force of friction is equal to that coefficient of friction, or mu, times the normal force. Now, our first example, coefficient of friction between a 20-kilogram wood block and a table is 0.3. The block is pulled across the table by a force of 12. What will be the block's acceleration? So we're going to draw a free body diagram of this thing. Okay, so it is a 2-kilogram wood block. It says there is a force pulling it forward of 20 newtons, or 12 newtons, excuse me. Okay, we know there's going to be a friction force because we have this coefficient of friction. So we're going to put that there is a friction force back here. We're not going to put the 0.3, okay, because that's not the force of friction. Then we also know there's gravity acting down on it. And it's going to be m times g, so 2 times 10 is 20 newtons. And there's a normal force pushing up from the table that's also going to be equal to 20 newtons. Now, we have to find this friction force using the new equation. So the way this reads, the coefficient of friction between the block and the table is 0.3. So this is our mu. So we're going to find the force of friction using this new equation. The mu is given as 0.3, and the Fn is 20 newtons. And when we multiply that together, we're going to get a force of friction of 6 newtons. So now I can put that right on here. So this is going to be 6 newtons for the force of friction. Now we have our free body diagram drawn and all of the forces figured out. The next step is always to do an F net equation. So F net equals ma. The 20 down for gravity is going to cancel the 20 up for the normal force. And then for our net force, we have 12 pulling it right, 6 pulling it left. They're in opposite directions, so we're going to subtract. The mass is 2 times A. And when we solve this, we're going to end up with A is 3 meters per second squared. So they are essentially the same problems we've been doing, except in order to find the force of friction, you're going to have to use this equation. Now, to complicate matters slightly, there is static friction and kinetic friction. Static means not moving, so static friction is friction when it's not moving, and then kinetic friction is when the object is already moving. It turns out that static friction is always greater than kinetic friction. There's more friction when something's sitting still than when it's moving. I think of this as like you're trying to move a big dresser, right? And the dresser is on a carpet and it's sunk down into the carpet. So when you try to push it, it's really hard to get it moving, okay? But once you get it moving and it's popped out of the little holes in the carpet, then it's going to slide a lot easier. So it's harder to start it moving because there's more friction than it is to keep it moving. And so for any surface, there's going to be two values of the coefficient of friction, mu. And the static coefficient of friction is going to be greater than the kinetic coefficient of friction. So we have an example of that at the top of the next page. All right, coefficient of friction between a 20 Newton block and a table are, okay, here's the static one, here's the kinetic one. Static is bigger than kinetic. In part A, it says what force is necessary to start it moving. When you see to start it moving, that means it's at rest, and we're going to use static. So for part A, we're going to do, actually I'm going to draw a little free body diagram. For our free body diagram, it says we have a 20 Newton block. All right. Now be careful, they gave you 20 newtons, they're actually giving you the force of gravity this time. So the force of gravity is 20. And then our normal force is going to be 20. Okay, we're going to put some force on it forward, and we have to overcome this static friction going backward. So we'll do this equation. F is mu Fn. Since we're just starting it to move, we're trying to overcome the static friction, we're going to use a static coefficient here. So it's going to be 0.4. Fn is 20. And our force of friction is going to be 8 newtons. So as long as this force is greater than or equal to 8 newtons, we can start it moving. Then for part B, we want to keep it moving. So we want to keep it moving, we're going to use the kinetic. And it says at a constant speed, we should remember constant speed means that the forces all cancel. So if the forces are going to cancel, that means F forward has to equal FF backward, then it will move at a constant speed. So again, we're going to use the same equation. The only difference is now we're going to use the kinetic version. So it's going to be 0.25 times Fn was 20, and that's going to give me a value of 5 newtons. So the forward force has to equal the force of friction is equal to 5 newtons. So in order to keep it moving at constant speed, we only need a force of 5 newtons, as opposed to start it moving to a force of 8. Our last example, we have a 2 kilogram block being pulled by an 18 Newton force as shown below, and then we got a coefficient of kinetic friction is 0.4, and we want to find the acceleration. This is as hard a problem as you can get, okay? Now, if I look at this, I'm going to start thinking about what forces are acting on it. I'm going to have gravity down. Okay, I got this 18 pulling it up and to the right. I'm going to have a normal force up, and I'm going to have a force of friction back this way. Now, I got these problems wrong when I was in college doing this stuff because I always wrote Fn is the same as gravity. So I would have put 20 in for the Fn. I did that for like 2 or 3 days, and I kept getting problems wrong, and I couldn't figure out why. Fg and Fn don't have to equal each other, and here's a case where they're not going to. Okay, if I look at this 18 newtons, and I'm trying to move this way, all right, that's not an x force or a y force, it's a combination. So I'm going to have to find the x component and the y component of this thing, okay, before I do the problem. So Fx, if I look at it, my hypotenuse is 18, x is the adjacent side, so Fx is going to be 18 for adjacent side. I use cosine of 30, and that's going to give me a value of 15.6, and Fy is going to be 18 sine 30, which is equal to 9. So now I know this is 15.6, and this is equal to 9. Now, here is why the Fn isn't going to equal 20 this time. It's not moving up or down, so the up forces and the down forces have to cancel. So we can write our y forces cancel. All right. So the 9 and Fn are pulling up, and the Fg is pulling down. So those up forces have to cancel the down forces. So Fn plus 9 has to equal 20, which tells me that Fn is 11 in this case. So now I can even put that on there. Fn is 11 newtons. All right. Now we can use that to find the Ff. So our next step, we're going to do Ff is mu Fn. Mu is the coefficient of friction, is this 0.4. So that's 0.4 times 11, which is going to give me 4.4 newtons. So I can write that on here too, equals 4.4 newtons. Okay, now we have our free body diagram drawn. We have numbers on all the forces, so we can do F net equals ma. So F net equals ma. So the up and down forces cancel each other. I'm just left with forces to the right and forces to the left. This thing is going to move to the right, so we're going to have 15.6 for this force minus 4.4 for the friction equals the mass of 2 times the acceleration a. Now, this is going to give me 11.2 equals 2a. So a is going to end up being 5.6 meters per second squared. Now that was kind of a tricky problem because we had to use the Ff is mu Fn equation, which is new to you today, and then also the fact that this Fn did not balance gravity. We had to figure it out.